Okay, so in the past couple of classes we've been talking about reactions that are thermodynamically favored or spontaneous, and considerations that make a reaction thermodynamically favored. And we ended up with this equation, delta G equals delta H minus T delta S, where delta G is the free energy, delta H is the change in enthalpy, and delta S is the change in entropy. So we know that in general, negative delta H's and positive delta S's predict a spontaneous reaction, or one that's thermodynamically favored. We call these the driving forces behind the reaction. A negative delta H drives delta G to be negative. A positive delta S drives delta G to be negative. So that's what we mean when we say driving force. So when we start looking, we know that delta H and delta S can both be either positive or negative. So when we take the combination of signs and values, we can kind of make qualitative predictions about what's happening in different situations. So here we have our equation, delta G equals delta H minus T delta S. In this case, case number one, delta H is negative, delta S is positive. What that means is that delta G is always negative, no matter what temperature I happen to be at. Delta G will be a negative number, because when I look at the signs of this reaction, if this is negative and delta S is positive, this whole thing is going to be negative. So we say those reactions are always thermodynamically favored if we look at that combination of signs. And if we were just looking at those signs individually, we would predict negative delta H, oh, that's a thermodynamically favored. Positive delta S, oh, that's thermodynamically favored. So that's case one. In case four, where I have a positive delta H and a negative delta S, each one of those individually predicts a non-spontaneous reaction, or one that's not thermodynamically favored. And mathematically, I'll always get, if this is positive and delta S is negative, no matter what T, because remember this is Kelvin temperature, no matter what Kelvin temperature I put here, delta G can only ever be positive. So in case four, when we look at just the signs, we predict that this will never be spontaneous. This will never happen as written. So now we have cases 2 and 3 where both signs are the same. And when both signs are the same, we get opposite predictions, whether we're looking at delta H or delta S. If they're both negative, we would predict by delta H that it's thermodynamically favored, but delta S would say not thermodynamically favored. So in order to figure out what's going on, we have to go back to our delta G equals delta H minus T delta S equation. So in the case where both signs are negative, delta H favors the reaction. Delta S does not. So in order to minimize the effect of the negative delta S, if we make T a small number so that this whole term is smaller than delta H, we can get a negative delta G. So in the case where both signs are negative, both delta H and delta S are negative, we say that that reaction is thermodynamically favored at a low temperature. So the higher temperature, I'll get to the point where the reaction can go from being favored to not favored if the temperature is high enough. So that's one combination. In that case, since they predict opposite things, if I do get a delta G that is negative based on the actual values I put in here, I would say that this is an enthalpy-driven reaction, because enthalpy predicts that it will be spontaneous or thermodynamically favored, and it actually is when I solve for delta G. Likewise, in case 3, where they're both positive, delta H predict not thermodynamically favored. Delta S, you predict it is thermodynamically favored. So in this case, I want this term to be the one that predominates. So if I make T big enough, I can make the delta S term drive delta G to be negative. So in this case, at high temperatures, reactions are spontaneous, and at low temperatures, they're non-spontaneous or not thermodynamically favored. So there's a whole set of questions you can ask qualitatively about what's driving the reaction, which means which sign, if I know that this reaction is thermodynamically favored, by looking at the signs, I can tell what is actually driving the reaction. Is it enthalpy, is it entropy, or are both of them making that reaction thermodynamically favored? Now, let's look at this one. Okay, I want to calculate the boiling point of H2O liquid going to H2O gas. So you need to remember back to first year chemistry, when you have a phase change, you have no temperature change because you have both liquid and gas existing. So this is an equilibrium situation. If I stay at the boiling point and maintain a constant boiling point temperature, I will set up an equilibrium between liquid and gas. So I can start by using delta G equals delta H minus T delta S. And then I say, well, if I'm at the boiling point, I'm at equilibrium. So delta G for this reaction is 0. And that's equal to delta H minus T delta S. Okay, so the next thing I can do is if I add T times 0.118 to both sides, I get T 0.1188 equals 44. So the temperature equals 44 divided by 0.1188, which equals 370, because really I can only have two significant figures there. So 370 Kelvin. The book value for that is 373. So it's pretty close. And again, that's going to depend on how I measure these two numbers, the heat of vaporization and the delta S of vaporization. But that's how you can go about doing something like that.